All right, all set up and ready to record, so hooray. Anyway, in this video, I just want to do a really quick overview of this activity slash project 8, just to kind of answer any questions that may come up along the way. So the front side of this thing is fairly generic in that we're just going to play around with some merge sort and some quick sort. I'm giving you some nice little lists that are currently not sorted, and I just want you to kind of sketch out how these particular algorithms are going to work. So in the merge sort, obviously, you're going to chop this thing in half, which is probably what, 1, 2, 3, 4, 5, 6, 7, 8. So you would chop these things into the two nice little bins of 8. Then you chop those 8s into 4s, the 4s into 2s, and ultimately end up with all of these nice little singletons. And then you'd start that zipping process as you kind of merge these things back together. In parts B and C, you're going to be doing basically the same thing, except for we're going to switch up algorithms. So here we're going to be playing around with quicksort. Wow, that looked like a tiny little strikeout. Let's change the colors and make it a little bit bigger. All right, so we're going to look at quicksort in both of those. Obviously, within quicksort, we're going to need to randomly grab some pivots. So the first one, I'm going to have you choose the pivot as being the middle value. So on your first go, you're going to be able to choose basically either the 11 or the 8 as your middle because the list is of length 16. So you can either take that one or you can take that one to be your middle. It actually probably runs a little bit smoother if you choose 8, just because 11 is a fairly large number in this list. But you'll choose the pivot, make your list to the left, make your list to the right, keep on choosing pivots as you go until you get the nice little singletons, and then you're going to concatenate these things all back together and have a nicely sorted list. Down in part C, you're going to be doing the exact same thing, except for you're going to constantly choose the first entry in the list as being your pivot. So grab the 7, make a list of things that are less than 7, make a list of things that are greater than or equal to 7, and then again, rinse and repeat that process over and over and over again. So here I just want you to kind of sketch out how it's going to go down. Then in part D, I want you to actually go ahead and try to implement a couple of these things. Here you're allowed to use whatever language you want to work with. So on D2L, I have a couple links to some implementations in Python. So if you just want to play around with those or improve or implement those ones, you totally can. If you want to take that pseudocode or that code and then redo it in C or C# or C++ or whatever language you want to, you can totally do that as well. When you're done with it, just give me a copy of your code as well as some screenshots of it actually running, or you can actually take your code, dump it into the little replit link or replit link, and give me a link to that so I can kind of see it operational as well. So the backside of this thing is where things start to get what I think to be a little bit more fun and a little bit more interesting. So in question 2, we are going to be, again, doing some list manipulation, except for the goal is to find a specific number in a list of, let's say, length n. And the way that we're going to find this number is by basically chunking this thing into 2 specific little bins and then asking, is the thing in one of the bins? Some game maker is then going to basically agree or disagree with what's happening. So what's going to emerge is they're going to think about having, let's say, 8 cards, and they're all going to be flipped over right now. And you're going to walk up to this game maker and be like, okay, I need to find the special card. So then from those 8, you're going to basically have a left side and a right side. And you'd say, okay, is the special little number in the left side? And then the game maker, if they're being truthful, will tell you correctly if it's there or not. So in this first little example, we're going to start with those numbers. So 1374265. So the idea here is that I don't actually know what the numbers are. So I'm going to basically chunk this thing in half. And I'm going to ask, okay, is this magic number, which I'm assuming to be a 4, whoa, which I'm taking to be a 4 right now. So I'm going to ask, is that magic little 4 in the left side? The game maker is then going to answer truthfully and say, yes, the 4 is on the left side. So I don't have to worry about the things that exist on the right side anymore. Then we're going to rinse and repeat that process again. So now I have a new list that is shorter. So there are 4 things only now. I'm going to chop this unknown list in half. And I'm going to again ask the game maker, is the 4 in the left side? And they would say no, because the 4 is in fact on the right side of that thing. So I would see that it's going to chunk down to a 7 and a 4. And then my very last question is going to say, Is the 4 on the left side? And the game maker would say no, because the 4 is in fact on the right side, which means that I can actually find the special little card. So if you view this as 8 hidden cards initially, if my goal is to find the magic one, I had to ask 3 questions. Initially, I had to ask, is it on the left side of the first list? Then I had to ask, is it on the left side of the second list? Then I had to ask, is it on the left side of my final little list of 2 things, which actually then gives me my final answer. So that list was of length 8. 8 is in fact 2 cubed. So the number of questions or queries that it had to use is then going to be that little exponent, which if I write that in fancy logarithms is then going to be log base 2 of that number n. If my list is of length 16, which you're going to see is 2 to the 4th, we're going to have to ask this question of, is it on the left side 4 times? So you'd chop it in half, chop it in half, chop it in half, and then finally you're going to get down to the little twosies. Once you get down to 2 things, if you ask, is it on the left, you automatically know what the answer is going to be. So if it is on the left, you know where it is. If not, you know to switch on the other side. So up in this little block of pseudocode, I have an implementation of that little game unfolding. So you're going to keep on doing this thing over and over and over again. So what's going to happen is you're going to take your initial list, rip it into a left side, rip it into a right side, and then ask, is X in list 1? So if that occurs, then you're going to recursively call this function again, but now on the left side. And you're going to keep doing that over and over and over. If I fail at my little number being on the left side, then it's going to grab it with the right side. So it's exactly that little process that we ran here. So I said, is it on the left? So that would say, is 4 in the left list, which returns true. So then my list becomes this. Then I say, is 4 on the left side of that? The answer would be no. So I would run it on the right side. Then I would say, is 4 on the left? They'd say no, which means that my 4 has to in fact be on the right. So it's kind of a cute little game. It's not really that complicated, but it is kind of fun to play with. Things get a little bit more interesting in question 3, which is where we're going to deal with a little bit of possible uncertainty. These type of questions I love just because they're fun. They're small little modifications to traditional games that may in fact blow up our particular algorithm, or maybe our algorithm can easily accommodate these particular things. So what's happening in question 3 is that the game maker, so basically the person who's telling us, did this work or did this not work, is allowed to possibly lie, or maybe their answer is just not correct. And they're allowed to do this incorrect or lie exactly 1 time. So then our goal is to try to accommodate for this inconsistency or some type of issue that may come up along the way. This type of scenario will emerge a lot more later in the course once we start chatting about some error correcting codes and some information theory, is basically how do we actually kind of accommodate for non-perfect information. So I'm assuming everything is great. Down here, it's, well, what happens if one thing might be off? Can I easily identify the thing that's off and then smooth it out afterwards? Or do I have to basically start from scratch all over again? So one way to play this game of kind of fearing inconsistencies is to simply ask every single question twice. So the way that that's going to look is we're going to play it on the same little list of 8 things, and I'm just going to randomly introduce a lie along the way. So if I wanted to actually implement this thing, you could create a lie at some point in time, basically have a little random number generator that's going to say when the lie is going to happen. And then when it does, do it, and then don't allow the thing to lie ever again. And we'll kind of see what that looks like here. So what's going to happen is if I still do the chop this thing in half, I'm going to say, okay, game maker, is the 4 on the left-hand side? What they would then say is, let's say they say no. So then I would be initially thinking that this would be my list. And if I kept on working on downward, I'd get all the way to the end and I'd find out that there would be no 4. So instead, what I could do, so if I ask, hey, is the 4 on the left side? And if they say no, right now I'm thinking, okay, the 4 is on the right. So if I ask a second time, is the 4 on the left-hand side? They have to answer truthfully. So they would have to tell me, yes, the 4 is on the left side. I don't necessarily know which of those two things were the lie. I just know that a lie occurred. Basically, my first go told me that I should think that it's over here. So based off of my first question. And then based off of my second question, I think the 4 is over there. So if I ask a third time of, hey, is the 4 on the left-hand side? They have to answer truthfully and say, yes, the 4 is in fact on the left-hand side. And then from there, I can just go all the way down the rabbit hole as I would have seen initially. If the lie would have occurred the other scenario or the other direction, so if I chop this thing in half and I say, hey, is 4 on the left-hand side? And they say, yes. So right now, I'm thinking that 4 technically is going to be on the left-hand side, but that could have been the lie. So then I ask it a second time and I say, hey, is 4 on the left-hand side? And they say, no. So that makes me think that the 4 is on the right-hand side. So then I ask a third time, is 4 on the left? And they have to answer truthfully to say, yes, the 4 is definitely on the left-hand side. So that is kind of the way that this lie detection and then possibly kind of coming out of the lie is going to start up. You can actually see that the lie can happen whenever you want to. So in that one, I basically lied right away, but I could have gone, hey, is 4 on the left-hand side? And they say yes. And then I ask, hey, is 4 on the left-hand side? And they say yes. And I was like, okay, you didn't lie to me there. So then I ask again. So now I'm dealing with 1, 3, 7, 4. And then I say, hey, is 4 on the left-hand side of those? And they say no. And then I say, hey, is 4 on the left-hand side? And they say no. So then I'm left with 7 and 4. And then I say, hey, is 4 on the left-hand side? And they say no. And then I ask, hey, is 4 on the left-hand side? And here they can say yes, which means that I don't necessarily know which one it's on. So then I have to ask a third time, is 4 on the left-hand side? And they would say no, which would in fact tell me that the 4 is over on the right. So that took 2 initial questions to find out that it was actually on the left. Then it took me 2 more questions to find out it was on the right. And then ultimately it took me 2 plus the 1 to actually hone in on it being on that right side of that last list. So in total, that gave me 7 total questions to emerge. So 2 and 2 and 2, and then 1 final little plus 1. Whereas up above, this only took me 3 questions to actually identify where that little 4 happened to be. So the idea here is that we're basically doubling the number of questions. So we have 2 times the 3 from before, and then 1 final little pass to make sure we know exactly where it is. So the number of questions that we have to see here is then going to be 2 log base 2 of n, so that little power of 3, and then plus that little 1 at the very end. So what I want you to play around with is trying to do the same game over here. Introduce wherever you want the lie to be. I really don't care if you want to just kind of pretend that the lie happens right away and then just kind of hone in on what the solution is going to be. If you want it to be later on, you can kind of see how you're going to have to overcome those things, do a whole bunch of other crazy stuff as well. There is a nice, fun little divide and conquer approach to this as well. So if you want to explore how to do this a little bit more cleverly, you can take a peek at what I wrote down below, but I'll kind of give you a little bit of oversight into what's actually happening. So up above, we actually just kind of chunked this thing into 2 bins, a left and a right bin. What's going to start happening down below is we're going to start creating bins that have a little bit of overlap with one of them. So you can kind of think about, maybe I ask, is it in this bin? And I ask, is it in this bin? And there's a tiny little bit of overlap between the 7 and the 4. That may or may not be useful. That's kind of the goal of this bonus question, is that if you have an overlap, what does that possibly give you as you try to chunk this thing on downward? So that's kind of the fun little game that I have sketched out in option 2. It's kind of cute and it's worth poking around a little bit. I really, really like these kinds of questions because I think they're lots of fun, because they introduce a fun, novel twist to kind of a very generic question. And how you overcome that actually is sometimes really, really hard, in that it's just such a simple little error that can occur that might just blow up your entire systems. Basically, you realize how fragile having perfect information becomes, the moment you introduce some small little bit of error, then it kind of ripples across everything. So it's a thing always worth poking into when it comes to various implementations, is like, what happens if I would have an incorrect read or grab something wrong? Does everything blow up, or is it, it's not so bad? I can kind of smooth this out afterwards. So we'll see a couple more things like this throughout the course, just because they're fun and nice little one-offs. But here's kind of a nice sketch out of what I'm looking at in this particular one. So anyway, have fun. If you got any questions, let me know. I also did shoot you an email that had some extra little comments about this particular question, so take a peek at that as well.